Welcome everyone to this video we prepared for you as an update on the progress and ongoing work regarding the work we're leading in the project, and namely the energy engine. My name is Mathaios Panteli, and I'm leading the energy team with Dr. Eduardo Alejandro Martinez Esena, or Alex, as you know him. Our research team is composed in alphabetical order by Ruben Bravo, Jose Nicolas Melgor Gutierrez, and Wentao Zhu, who will also be presenting in this video on their work in this project. This is a quick overview of our progress and ongoing work, including updates on the software development of the energy engine, the case studies we have in the project, the optimization, the application of multi-objective optimization and the benefits that these applications can bring in the project, and the progress we made on the web interface and the training material we developed. We will be happy to follow up with more detailed discussions during the annual forum or in any bilateral meetings you may want to plan with us if needed. Now, the Python-based energy engine we developed, which we call HighEnergy, is a flexible open source optimization tool, and it is a very powerful tool which is constantly evolving, and it can be used in multiple key power system analysis applications such as economic dispatch, unit commitment, AC and DC power flow, detecting islands in the network, and so on and so forth. Also importantly, HighEnergy can model different new and emerging technologies, which are key both for the application in this project as well as power system in general, including hydropower, where we see and we include pump and run-of-the-river options, the integration and modeling of renewable energy sources such as solar and wind power, storage, and also the impacts of climate change on the operation and planning of power systems, including, for example, impacts of high temperatures and water scarcity on the generation, and in particular on the cooling of big thermal power plants. It is important to note that HighEnergy, it is a standalone model in the sense that it can be used independently if desired by energy engineers and for energy system planning and operation, but it is also flexible enough to be integrated and interact with the other models we have in the project. Also, a very important feature of our engine is that it is fully flexible and it can be fully customized to the needs and the priorities of the end user, depending on the study that they would like to run. As an example, we perform some studies on using a simplified version of the transmission network of Ghana, and we see that the model can model and it can also consider different scenarios and sensitivities, including, for example, water availability, renewables integration, stress on the network, and also the temperatures affecting the rating and the performance of power system assets. And we can define different levels of these sensitivities, for example, the base case, low, high, and as well. And we can also tailor the settings that we have in our engine, depending again on the expectations and the needs of the end user. For example, considering or not the power system network, if we want to run a fully adequacy study, considering or not the unit commitment, the network losses, hydraulic routing, cooling, and also importantly, the time resolution, depending on the type of studies that we would like to run. And for each of these scenario, each of the sensitivity and settings, we can define a set of metrics, which we see in the right-hand side figure in this slide, which includes, for example, the operating cost, the load shedding, as well, and very importantly, the computational cost. The computational cost, it is an important matter in our work, considering the complexity of the problem and the need for computational efficiency. So I will now pass it on to Nicholas, who will provide basically an update on the development of our engine and on our efforts to improve the computational efficiency of our algorithm. Nicholas?
Thank you, Matthias. Well, I will then start describing the development of the software development of the energy engine. Well, to start, basically we use initially to model or to formulate out mathematical problems. We use a tool called Pyomo. Pyomo is simply a collection of Python software packages that basically allow representing any mathematical problem in an easy way in a software platform. However, during the course of the project, we discovered that with Pyomo, we use a lot of time to run, to model, to formulate and execute the mathematical formulation, and finally to solve it. So because time is critical in our project, because we need to run several thousands of simulations in our optimization, we then decided to improve our solver and trying to use different tools to trying to speed up the software. In this case, the next step that we took to improve the computational effort of the engine is to use directly the solver GLPK. Pyomo was an interface, so instead of using the interface, we decided to formulate directly the mathematical formulation inside the solver called GLPK. After doing that improvement, we got a significant improvement in the computational time. However, it seems that it's not enough. So we took a step further, and we decided then to implement to use a new solver called CLP, which is another open source solver that basically seems to be that is stronger and is faster compared to GLPK, and also the new implementation has been developed in C++. With this new improvement or that we have done in the energy engine, we have been able to increase dramatically the speed of the solution speed of the solver. We will present another step to improve the speed of the solver or the speed of the solution. That is the reduction of networks. So basically, we develop a tool here, or we develop a module that allows reducing different networks or different different sizes and different voltage from one massive amount of buses and branches and basically a massive number in the power system to a small system, to a small number of buses and lines that allow us to solve the problem more effectively. In this case, we have an example with the network of Egypt. In the left side, we can see the full Egyptian network. The full Egyptian network has 2,896 nodes, 4,162 branches, and 569 generators. After the reduction, we ended with a network that is compounded by 69 buses, 254 branches, and 224 generators. As you can see in the left side, you can see that figure that is compounded by plenty of dots of different colors, and it seems to be connected like with a network there. That network, as you can see, if it is difficult to see, it is difficult to solve as well because it is quite big. Now, the network of the right side is easier to deal with, and then we can provide solutions quicker and more meaningful solutions as well, because we are taking the most meaningful parts of the network. So we did the same with the whole EAPP. Basically, in the whole EAPP, you can see in the left side, again, that we have the whole network is about 7,500 nodes, about 10,000 branches, and 1,400 generators. That's a massive network. Obviously, any solver can have difficulties to solve this kind of network because it's really big. So we use again the technique to reduce the network, and we ended having the network of the right side that basically has 747 nodes, 815 branches, and 1,450 generators. That in this case, we preserve almost all generators because we want to analyze the impact of each generator in the network. So finally, we will present then in this section, the software development, and also we will proceed then to talk about the different case studies that we are considering. We have considered three main case studies, in the East African Power Pool, Myanmar, and Ghana. The Eastern Africa Power Pool is compounded by 10 countries. It explains the big size of the network. And then in East Africa, we have applied basically tools like the network reduction, and we have fine-tuned basically the parameters that we have in the network to represent as accurately as possible the full network. We have also optimized that network using the DC optimal power flow, that basically takes a small amount of time to solve the reduced network that we have developed. Finally, in the ongoing work, we are doing a multi-criteria assessment of climate change on the resilience of EAPP in both national and regional levels. Now, for Myanmar, we have also applied the network reduction. Even if Myanmar is a small network compared with the EAPP, it's still difficult to deal. So we needed to reduce it as well. So we reduced it from 100 buses to 60 buses. We have also performed reliability studies in the Myanmar network using lighting hypercube and sequential Monte Carlo sampling. And the ongoing work is basically a multi-objective optimization planning for the future power network to achieve the minimal energy cost and carbon emissions while maximizing the reliability of the system. Now for Ghana, that is our more advanced case study, we have used reduction techniques. We have optimized the system using the DC optimal power flow. We have simulated the network using the alternate current power flow. We have made a combined simulation and optimization using the water and energy systems. And we also have a graphical representation of the network in a web interface. But to perform all these studies and obviously to realize or to finish the ongoing work, we need to develop then different tools. And in this case, one of the tools is the multi-objective optimization that Ruben will present after this slide. So I would like to give the word to Ruben.
Thank you, Nicolas. A useful tool to support multi-criteria decision-making problems that is under development is the integration of multi-objective optimization techniques in the energy model. The purpose of multi-objective optimization is to find a range of solutions, as you can see here, as diverse as possible, known as Pareto front, to simultaneously optimize several objectives. Then, because every solution is a candidate, and a posteriori decision-making process is required. Some benefit in the integration of multi-objective optimization in the FutureDAMS project are related to the analysis of synergies, trade-offs, and uncertainty quantification to support with data and detailed analysis decision-making processes. Multi-objective optimization has also interesting application in the FutureDAMS project, like transmission network planning, capacity expansion planning, resource allocation, and the study of interaction between different systems to support sustainable development. In the next slide, we can see an example of the application of multi-objective optimization in the power network expansion planning for Myanmar. The focus of this optimization problem is to select the best configuration, considering, for example, shown as variables, new power lines, new thermal power station, and new renewable power plant for the planning of the future power network infrastructure. In this case, we want to achieve a minimum investment cost and carbon emissions simultaneously while maximizing the reliability of the system. So here shown as the objectives. It should be clarified that this is an ongoing study. So here we show an example generated with simulate data. When the model is running, we expect to have a similar profile for the Pareto frontier, showing the solution that simultaneously optimizes the three objectives. So in this diagram, so this is a three-dimensional diagram shown in a two-dimensional scheme. We can see the trade-off between these conflicting objectives. The horizontal axis displays the demand curtailment, which is the quantification of the reliability of the system. The y-axis indicates the investment cost. And finally, the total carbon emission of each configuration is shown with different colors and also different size of the bubbles shown in the diagram. So every point in the diagram corresponds to a specific design of the future power network, and each axis of the diagram corresponds to each objectives that want to be optimized. So, for example, we can see that a highly reliable system. So, for example, if we want to in the x-axis to the 0, and the bubble shown in red, so we can see that a highly reliable system requires a high investment, and also its operation emits a high amount of carbon emission. For the other side, if we want to increment the penetration of renewables, so a low carbon emission, so a bubble shown in blue, that is related with high penetration of renewable, can be achieved with high investment, but also degrading the reliability of the system. So in this case, with this tool, we can handle the trade-off between different objectives. Finally, because every point is a candidate, and a posteriori multi-criteria decision-making process analyzing this trade-off between these conflicting objectives is necessary to select the best candidate according to this performance, these three objectives, or another performance that could be useful for the user of the model. We're also working on the Hydra web interface that will be presented next by Wentao.
Okay, thank you very much, Ruben. So in this slide, I will walk you through the main steps to access the online model. For the best user experiences when accessing the interface, we recommend you to use Firefox or Chrome. After you type in the URL, which is hydro.org.uk/login, you will be asked to input your login details, as shown in the screenshot on the left-hand side. For users who do not already have an account, click Create an Account and provide relevant information on registration, as shown on the right-hand side. To be noted, cookies must be allowed for users to access the dashboard. There are different options to access a network model. You can either contact the network model owner and provide your username, which is the email you used to log into the interface, or import the network data from a JSON file. For detailed information on instructions for accessing the online interface, and for navigating the dashboard and loading or creating network models, please refer to the training material that has been shared with you. Okay, in the next slide, the online training material is created using Adobe Spark, which is a web page format document that includes text, pictures, and videos. Online training materials are the energy simulator consists of four sessions. Each provides you with step-by-step guidance on accessing the simulator and on creating and editing your own network model. A few generic examples will also be provided to allow you to practice the skills acquired through online trainings. Finally, a practical example will be presented on the applicability to a real power system model. The links to access each training sessions have already been shared with you. Thank you very much, and I'll now hand over to Mathaios to conclude the session.
Thank you very much, Wentao, and everybody for your presentation. We hope we provided a quite high level of sufficient update of our work. And as I said in the opening of this video, we'll be very happy to follow up with any questions, comments, ideas, suggestions you may have to share with us. So please feel free to get in touch with either myself or Alex, and we'll be happy to follow up with more discussions either during the annual forum, or we can arrange a meeting to further discuss our progress and how we can tailor our applications towards the benefits of the project. Thank you very much.